Example 4. Find the derivative of the function fx equals absolute value of x at point x equals 0. So I guess just to give a little bit of a sketch, here's your absolute value function, and there's a point, right? We can still start with our first principles. And I'll just plug in the function. Okay. At this point, I would like to plug in the point x of 0 instead of finding the general derivative. So limit as h approaches 0, 0 plus h minus 0 over h. So equals limit h approaches 0. The zeros can go away, so just an absolute value of h over h. Now we gotta take it two different ways, because the absolute value function, you can have a negative side of it and the positive side of it. So think about it. With our graph here, if I'm approaching from the left side of my limit, you have a slope, like a negative version of it, right? So limit of h approaching 0 from the left side, you have a negative h over h, which is negative 1. If you're approaching from the right side, you're looking at, so approaching from the right side, you have a positive h over h, which is positive 1, just even by looking at my sketch. So my limit does not exist there, right? So limit does not exist, which means my derivative at 0 also does not exist. And we know because it's a cusp right at the point. Okay, one last example. Example 5. Determine the equation of the normal line to the curve y equals x over x plus 1 at this point x equals 2. So a normal line, this means a perpendicular line in math. Perpendicular. So if you can sketch it out, let's say you have a curve that looks like this, and there's a point there. A normal line would be like 90 degrees perpendicular, so if I had a tangent that looked, it's not very good, tangent that looked like this, a normal line would be exactly 90 degrees from your tangent. Okay, so this is your normal line. So you want to first figure out the slope of the tangent and then figure out the normal. Okay, start with my derivative at 2. So limit h goes to 0. Again, we're just starting with the first principles. Okay, limit h goes to 0, and let's plug in the actual function. So instead of x, we have 2 plus h. Instead of x, again, we have 2 plus h plus 1 minus f of 2, which is 2 over 2 plus 1. And again, I'm going to just put this over 1 over h to the side. Okay. We are going to simplify a little bit before we get to common denominators. Three plus h, 2 over 3. We are going to multiply 3 to my left side function and then, sorry, exponent. Nope, I'm blanking. And then I'm going to multiply 3 plus h to the right side to make the common denominator. So 3 times to the left side, and 3 plus h on the right side, and I have a common denominator, which is 3 times 3 plus h. Okay, so I just skipped a step of doing the common denominator. Let's expand and simplify. So 6 plus 3h minus 6 minus 2h. 3 times 3 plus h, and 1 over h. Cancel the 6 and the negative 6, and then let's put the h's together. Just one h left. And 1 over h, we're going to cancel the h's. And let's actually 7. Let h equal 0. So 1 over 3, 3 plus 0, which gives you 1 over 9. So the slope of my tangent is equal to 1 over 9. You need to know that any two perpendicular lines, their slopes are negative reciprocal of each other. So the slope of my normal line is going to be the negative, the minus sign, and flip this number, reciprocal, negative 9. We are going to figure out, I actually did a bit of work there, but my y value for the point of x equals 2 is equal to 2 over 3. So if I plug it in all into my linear equation, y equals mx plus b, to find b, I have 2 over 3 equals negative 9, my slope, times 2 plus b. 2 over 3 equals negative 18 plus b. which means if I add 18 to the other side, b will equal 56 over 3. So my final equation for that normal line will look like this. Okay, so there you have the normal line. I'm going to skip the last notation because we already looked at it at the top.